What if everything you see, the stars in the night sky, the ground beneath your feet, even your own reflection, is just a tiny fragment of a reality far stranger and more vast than you've ever imagined? It sounds like something from science fiction, but here's the mind-bending truth. Scientists estimate that a staggering 95% of the universe is completely invisible to us. This mysterious bulk of existence isn't made of planets, stars, or even atoms. It's something far more elusive, known as dark matter and dark energy. And yet, despite its invisibility, this hidden force shapes everything we know, from the way galaxies spin to the very fate of the cosmos itself. That's the paradox we're diving into today, the question of what really is everything. This isn't just about astronomy or physics, it's about the very nature of reality. Think about it. Every time you look at your hand, you're seeing a collection of atoms, but zoom in far enough, and those atoms dissolve into a chaotic dance of particles that flicker in and out of existence. The solid, predictable world we take for granted is, at its core, a shimmering illusion. And that's only the beginning. From the quantum realm, where particles can be in two places at once, to the cosmic scale, where galaxies are strung together like beads on an invisible web of dark matter, our understanding of everything is constantly being rewritten. So how did we get here? How did humanity go from ancient myths about the origins of the universe to uncovering clues about dimensions we can't even perceive? That's the journey we're about to take, a voyage through time, from the first philosophers who dared to ask what the world was made of, to the modern-day scientists probing the edges of reality with particle colliders and space telescopes. Along the way, we'll confront questions that challenge not just what we know, but how we know it, because the deeper we dig, the clearer it becomes. The universe is far stranger, more beautiful, and more mysterious than we ever dreamed. And the most thrilling part, you're about to see it all unfold. For thousands of years, humanity has grappled with one deceptively simple question: what is reality made of? The answers we've come up with couldn't be more different or more revealing. In the West, the dominant view has been materialism, the idea that everything boils down to physical matter, atoms, particles, the tangible stuff we can measure. But travel eastward, and you'll find traditions that turn this assumption on its head. Ancient Hindu philosophies speak of Maya, the illusion that veils true reality, while Buddhist teachings describe emptiness not as nothingness, but as the absence of fixed, independent existence. These aren't just poetic metaphors, they're profound challenges to how we perceive the world. And here's where things get eerie. Modern quantum physics is starting to sound a lot like these ancient ideas. Take Schrödinger's famous cat alive and dead at the same time until someone looks. This isn't just a quirky thought experiment. It suggests that reality might not exist in a fixed state until it's observed. In other words, the very act of measurement could be what solidifies the world around us. It's as if the universe is a cosmic choose-your-own-adventure book, with countless possibilities hovering in potential until we turn the page. This blurring of observer and observed forces us to ask, is reality something we discover or something we create? Now, consider the implications. If the bedrock of existence is this uncertain, how do we make sense of anything? That's where mathematics enters the picture, not just as a tool, but as a possible blueprint for reality itself. From the elegant equations of general relativity to the strange symmetries of particle physics, math has an uncanny ability to predict how the universe behaves, almost as if it's the hidden language of existence. Could numbers and patterns be more fundamental than matter? It's a tantalizing clue that the next piece of this puzzle might lie not in a telescope or a microscope, but in the timeless truths of pure logic. Mathematics has always held a strange power, not just as a tool for counting or measuring, but as something far deeper. Over 2,000 years ago, Pythagoras stood on a beach, watching waves lap against the shore, and had a revelation. The patterns of nature could be described in numbers. To him, mathematics wasn't just useful, it was the hidden fabric of reality itself. Fast forward to today, and modern physics seems to echo his ancient intuition. Equations predict the existence of particles before we detect them, describe black holes we've never seen, and even suggest the possibility of unseen dimensions. It's as if the universe runs on an operating system written in numbers. Take something as simple as pi. This never-ending number, the ratio of a circle's circumference to its diameter, appears everywhere in the spirals of galaxies, the orbits of planets, even the way rivers twist and turn. Or consider the Fibonacci sequence, where each number is the sum of the two before it. You'll find this pattern in sunflower seeds, hurricanes, and the curl of a nautilus shell. It's almost eerie how these abstract ideas emerge in the natural world. Einstein once marveled at this, asking how mathematics, a product of human thought, could describe the universe with such uncanny precision. This raises a profound question. Is math something we invented or something we discovered? Some argue that numbers and equations are human constructs, tools we created to make sense of chaos. Others believe they're eternal truths, waiting to be uncovered like explorers stumbling upon a hidden continent of pure logic. String theory, for instance, relies entirely on complex equations to propose that tiny vibrating strings underlie all matter. But here's the catch. These strings exist in dimensions we can't perceive, making the math our only window into their existence. Yet even mathematics hits a wall when we enter the quantum realm. Particles vanish and reappear, communicate instantaneously across vast distances, and exist in multiple states at once. No equation fully explains why, only how. It's as if reality itself flickers between order and chaos, teasing us with glimpses of a deeper logic we haven't yet grasped. So perhaps the answer lies not in choosing between discovery or invention, but in realizing that mathematics is the closest thing we have to a universal language, one that's still teaching us how to listen. If you've ever dropped a pebble into a still pond and watched the ripples spread, you've witnessed something strangely similar to one of quantum physics' most baffling experiments. Picture this: scientists fire tiny particles, electrons, photons, even entire molecules, one by one at a barrier with two slits. Common sense says they should pass through like bullets, leaving two neat clusters on the detector behind. But that's not what happens. Instead, over time, the particles create an interference pattern, a series of light and dark bands that only make sense if each particle is behaving like a wave, passing through both slits at once and interfering with itself. Here's where it gets weirder. The moment you place a detector to observe which slit the particle actually goes through, the interference pattern vanishes. The particles, as if aware they're being watched, suddenly act like well-behaved bullets again. This is the heart of quantum superposition. Particles existing in multiple states simultaneously until measured, like a spinning coin that's neither heads nor tails until it lands. Richard Feynman wasn't exaggerating when he said, "If you think you understand quantum mechanics, you don't." Now imagine two coins spinning in perfect sync, no matter how far apart they are. Flip one to heads and the other instantly becomes tails, even if they're on opposite sides of the galaxy. That's quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. It's not magic, it's a fundamental feature of reality where particles remain mysteriously linked, sharing information faster than light could ever travel between them. What if these microscopic oddities aren't just quirks of tiny particles? Some theories suggest superposition and entanglement might operate on cosmic scales, that the entire universe could be a vast, interconnected quantum system. After all, every atom in your body was forged in the hearts of stars, entangled across billions of years. Maybe the fabric of reality isn't just strange at the quantum level. Maybe strangeness is the fabric. The idea that our three-dimensional universe might just be an illusion, a projection from a two-dimensional surface, sounds like something straight out of the Matrix. But this isn't science fiction. It's a serious theory in physics called the holographic principle. Picture a credit card hologram, a flat surface that somehow holds all the information needed to create a shimmering, three-dimensional image. Now imagine that on a cosmic scale where the entire universe, with its galaxies, stars, and even you, is encoded on a distant, two-dimensional boundary we can't see. It's a mind-bending concept, but it emerges from one of the most stubborn puzzles in physics. What happens to information that falls into a black hole? According to Einstein's equations, black holes should erase everything that crosses their event horizon. Violating a fundamental law of physics, information can't just disappear. But in the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that the surface area of a black hole's event horizon, not its volume, determines how much information it can hold. In other words, all the data about what's inside every atom, every particle might be smeared across its boundary like a cosmic hard drive. Stephen Hawking later showed that black holes slowly evaporate, raising the question, where does that information go? The holographic principle offers a solution. Maybe it was never inside the black hole to begin with. Maybe it was always stored on the surface, projected inward as the illusion of a three-dimensional space. Now stretch that idea to the entire universe. If a black hole's interior can be described by information on its edge, could the cosmos itself be a grand hologram? Some theorists argue that the fabric of reality might work the same way, that everything we see, touch, and experience is a projection from a hidden, two-dimensional layer at the edge of space-time. It's not just wild speculation. Certain calculations in string theory and quantum gravity suggest that the math works out. In fact, in some models, the equations describing a three-dimensional universe and a two-dimensional one turn out to be mathematically equivalent, like two sides of the same coin. This leads to an even more unsettling possibility. If the universe is a hologram, could it also be a simulation? Philosophers like Nick Bostrom have argued that if advanced civilizations ever develop the power to create hyper-realistic simulations of their ancestors, the odds are overwhelming that we're living in one of them. After all, how could we tell the difference? The holographic principle doesn't prove this, but it does blur the line between reality and information in a way that makes the simulation hypothesis feel less like fantasy and more like a legitimate question. But here's the twist. What if consciousness is the key to unlocking this mystery? Quantum mechanics already suggests that observation plays a strange role in shaping reality. Now combine that with the holographic idea. If the universe is a projection, who or what is the projector? Some interpretations of quantum physics propose that consciousness itself might be the mechanism that collapses possibilities into concrete reality, like a cosmic observer tuning the hologram into focus. It's a controversial idea, but it bridges the gap between ancient philosophies that saw mind and cosmos as inseparable and modern physics, where information and perception seem to shape the very fabric of existence. So are we living in a hologram, a simulation, or is reality something even stranger, where the observer and the observed are entangled in ways we're only beginning to glimpse? The holographic principle doesn't just challenge our understanding of space and time, it forces us to reconsider what it means to be at all, and that might be the most profound mystery of all. Consciousness might be the most mysterious ingredient in the recipe of reality. Think about this. In quantum experiments, particles seem to know when they're being watched, changing their behavior under observation like shy actors on a stage. This isn't just a quirk of tiny particles, it forces us to confront a startling possibility. Could the act of observation itself be what brings reality into focus? Some interpretations of quantum mechanics suggest exactly that. Without a conscious observer, the universe might remain a blur of probabilities, like a film reel waiting for a projector's light. Now take this idea beyond the lab. Studies on meditation reveal that trained practitioners can alter their brain waves, even influencing physical matter in subtle ways. The placebo effect shows us how belief alone can trigger real biochemical changes. Patients given sugar pills sometimes heal as if they'd taken actual medicine. Then there are near-death experiences where people report vivid, coherent awareness during clinical death, moments when their brains show no measurable activity. These phenomena don't fit neatly into a purely materialist worldview, where consciousness is just a byproduct of neurons firing. This clash of perspectives is where things get fascinating. On one side, materialists argue that everything, thoughts, emotions, even the sense of self emerges from physical processes in the brain. But panpsychism, an ancient idea gaining modern traction, flips that assumption. What if consciousness isn't something the brain produces, but a fundamental feature of the universe itself? In this view, even atoms might possess a faint glimmer of awareness, like drops of water reflecting the ocean. It's a radical notion, but it echoes themes found in indigenous cosmologies and Eastern philosophies, where mind and matter are deeply intertwined. So where does that leave us? If reality is shaped by perception, does the moon exist when no one's looking? Philosophers have wrestled with this for centuries, but now physics is weighing in. The double-slit experiment hints that unobserved particles exist in a ghostly state of maybe. Only when measured do they snap into definite positions. Could this mean that consciousness isn't just a passive witness, but an active participant in creation? And if consciousness shapes reality, what does that say about time? We experience it as a steady flow, but physics treats it as just another dimension, malleable, perhaps even illusory. Could our perception of time be the next layer of the illusion, a story the mind tells to make sense of a far stranger truth? Time behaves less like a steady river and more like a chameleon changing its colors depending on where you look. Near a black hole, for instance, gravity warps time so severely that a single hour for someone near the event horizon could stretch into decades for an outside observer. Imagine two astronauts. One ventures close to a black hole while the other stays far away. When they reunite, the first might have aged mere minutes while the other has lived through years. This isn't science fiction, it's Einstein's theory of relativity in action, proving time is elastic, bending under the weight of gravity like a trampoline under a bowling ball. Now zoom into the quantum realm and time gets even stranger. Particles don't just ignore our everyday rules, they seem to sidestep time altogether. In quantum experiments, particles can appear to influence events in their own past, a phenomenon called retrocausality. It's as if the universe's script isn't written in chronological order, but edited out of sequence, with effects sometimes preceding causes. This bizarre behavior has led some physicists to propose the block universe theory, where past, present, and future all exist simultaneously, like frames in a film strip. In this view, our sense of time flowing is just an illusion, a trick of perception as we move through the block, frame by frame. ever experienced déjà vu, that eerie feeling you've lived a moment before? Or a dream that later unfolds in reality? These glitches in our temporal perception might be more than misfires in the brain. Some researchers speculate they're fleeting glimpses of the block universe, where the boundaries between then and now blur. Even precognition, the sense of knowing future events, has been studied in labs, with results that challenge conventional notions of linear time. Of course, skeptics argue these are just quirks of memory and probability. But what if time isn't a fixed backdrop to the universe, but a tool our minds use to make sense of chaos? This raises a radical question. Is time real, or just a useful story we tell ourselves? Ancient cultures like the Hopi language lacked tenses for past and future, speaking of events as interconnected, not sequential. Modern physics seems to echo this. Equations often work equally well whether time flows forward or backward, suggesting it might not be fundamental at all. Think of a movie played in reverse. The laws of physics don't care, only our subjective experience does. Now pivot to the fabric of space itself. If time is malleable, could space be too? Wormholes, those hypothetical cosmic shortcuts, could thread distant points in space-time together like holes in a folded piece of paper. String theory goes further, proposing that extra dimensions might be curled up invisibly around us. The universe's structure, then, isn't just a static stage. It's dynamic, even alive with possibilities. And just as time might be a construct, so too could the very space we move through be part of a deeper, more mysterious geometry waiting to be decoded. The idea of empty space seems simple enough, just a vast, silent void between stars. But dive into the quantum world, and that emptiness comes alive, crackling with energy like static on an old television screen. This is the quantum foam, a seething ocean where particles and antiparticles constantly pop into existence, only to annihilate each other in bursts of energy so fleeting they defy measurement. Imagine a bubbling pot of water, but instead of steam, its entire particles appearing and vanishing trillions of times per second. These quantum fluctuations aren't just theoretical, they've been detected in experiments like the Casimir effect, where two metal plates placed microscopically close in a vacuum inexplicably push toward each other, squeezed by the riotous energy of this so-called empty space. For centuries, Newton pictured space as an unchanging stage, a rigid grid where objects moved predictably. But Einstein shattered that illusion. His theory of general relativity revealed that space isn't just a backdrop. It's a dynamic fabric, warped by mass and energy like a trampoline sagging under a bowling ball. Planets don't orbit the sun because of some invisible force. They are following the curves in this cosmic fabric, like marbles spiraling around a funnel. Even time bends along with it, slowing near massive objects. This interconnected mesh of space and time-space-time is anything but static. It breathes, ripples with gravitational waves, and stretches under the influence of something even more mysterious: dark energy. Speaking of stretching, here's the cosmic plot twist. The universe isn't just expanding, it's accelerating. Galaxies are racing apart faster and faster, as if some invisible hand is pressing down on the gas pedal of reality. That hand is dark energy, a force making up nearly 70% of the universe's total energy. Unlike gravity, which pulls things together, dark energy pushes space itself apart. But what is it? One leading theory suggests it's the energy of the vacuum itself, the same quantum foam we started with. If empty space isn't truly empty, but brimming with this latent energy, could dark energy simply be the cumulative hum of countless quantum fluctuations? Now let's flip the question. If space isn't empty, what is it filled with? Ancient philosophers like Aristotle argued for the plenum, a universe with no true void, only varying densities of substance. Modern physics might be circling back to that idea. Between quantum foam, dark energy, and the invisible scaffolding of dark matter, which we'll explore next, the nothingness of space looks more like a cosmic symphony, vibrating with forces we're only beginning to hear. The deeper we probe, the clearer it becomes. The universe abhors a true vacuum. Even in the darkest voids between galaxies, the fabric of reality is alive with potential, whispering secrets about the true nature of existence. Galaxies should fly apart. That's the unsettling conclusion astronomers reached when they first measured how fast stars orbit at the edges of spiral galaxies like our Milky Way. The outer stars whip around so quickly that the visible matter, stars, gas, dust simply doesn't provide enough gravity to hold them in place. Without some invisible anchor, these galaxies would have torn themselves apart billions of years ago. Yet here they are, spinning gracefully as if guided by unseen hands. That missing mass is dark matter, an elusive substance that outweighs regular matter 5-to-1, sculpting the cosmos from the shadows. One of the most striking proofs comes from cosmic collisions, like the Bullet Cluster. When two galaxy clusters slammed into each other, their visible gas heated up and stalled in the middle, while their dark matter, revealed by gravitational lensing, plowed straight through like ghostly freight trains. The dark matter's gravity bent the light of distant galaxies behind it, creating eerie, stretched images in space. This wasn't just indirect evidence, it was a cosmic fingerprint, showing dark matter's gravitational grip without a single photon of light. So what is it? The leading candidates sound like science fiction. Weakly interacting massive particles, or WIMP, are hypothetical heavy particles that barely touch ordinary matter, drifting through you right now like cosmic neutrinos. Then there are actions ultralight particles born from quantum field theory, so tiny that trillions could pass through a needle's eye every second without a trace. Some experiments hunt for these phantoms in abandoned mines, where detectors wait for the rare ping of a dark matter particle bumping into an atom. Others look for faint signals from space, like gamma-ray excesses that could be actions decaying. But here's the wildest twist. Dark matter might not be a particle at all. Some theories suggest it's evidence of parallel universes' gravity leaking into our cosmos from dimensions we can't access. Imagine our universe as a sheet of paper floating near another. The subtle tug between them could manifest as this invisible mass. It's a radical idea, but it underscores how little we truly know. And if dark matter is the hidden glue holding galaxies together, its counterpart, dark energy, is the mysterious force tearing the universe apart at the seams. Together, they paint a humbling picture. The cosmos we see is just the faintest shimmer on the surface of a much deeper, darker ocean. Imagine blowing up a balloon, watching its surface stretch thinner as it expands. Now picture that balloon is the universe, and every dot on its surface is a galaxy racing away from the others. This isn't just expansion, it's accelerated expansion, as if some invisible force is pumping the balloon faster and faster. That force is dark energy, the universe's mysterious accelerator, pushing galaxies apart so fiercely that it overrides gravity's relentless pull. The irony. Einstein almost predicted it. In 1917, he introduced the cosmological constant, a mathematical fudge factor to keep the universe static, balancing gravity's tug with a subtle repulsive force. When Edwin Hubble later proved the universe was expanding, Einstein called it his biggest blunder. But decades later, astronomers discovered the expansion wasn't just continuing, it was speeding up. The cosmological constant was resurrected overnight, rebranded as dark energy. Now, it's the leading explanation for why the cosmos is flying apart at an ever-increasing rate. So what's the end game? If dark energy stays constant, the universe faces a big freeze, a slow, cold death as galaxies vanish over the horizon, leaving isolated islands of stars to burn out in an ever-darkening void. But if dark energy grows stronger over time, the outcome is far more violent, the Big Rip. In this scenario, dark energy's grip would intensify until it tears apart galaxies, then solar systems, then atoms themselves, shredding the fabric of reality. Here's where it gets stranger. Dark energy might not be a thing at all, but a property of space itself. Quantum physics suggests that empty space isn't truly empty. It's a frothing sea of virtual particles popping in and out of existence. Each fluctuation carries energy, and if you add up all that energy in the vastness of space, you might get dark energy. But there's a problem. The calculated value is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science. Could the answer lie beyond our universe? Some theories propose dark energy is a signature of the multiverse, a cosmic fingerprint from neighboring universes with different physical constants. In this view, our universe's expansion rate isn't special. It's just one of countless possibilities, like a single bubble in an infinite foam. It's a humbling thought. The fate of everything we know might hinge on forces entirely outside our reach, echoing in dimensions we'll never see. What if our universe is just one page in an infinite cosmic library, where every possible version of reality exists simultaneously? This is the tantalizing promise of the multiverse, a concept that stretches the boundaries of imagination while challenging the very definition of existence. Take eternal inflation, a theory where our universe is a single bubble in a frothing sea of space-time. Picture an endlessly expanding ocean, with new universes constantly budding off like bubbles in champagne, each with its own unique physics. Some might have stronger gravity, others faster light or no light at all. In this view, the Big Bang wasn't a one-time event, but a local hiccup in an eternal, self-replicating cosmos. Now shift gears to the quantum realm, where the many worlds interpretation offers a different kind of multiverse. Every time a quantum particle faces a choice like whether to spin left or right, the universe splits. One version of you sees the particle spin left, another version, in a parallel timeline, sees it spin right. This isn't science fiction, it's a mathematical consequence of Schrödinger's equation. Thought experiments like quantum suicide take this further. If you set up a device that kills or spares you based on a quantum event, there's always a timeline where you survive, creating the eerie illusion of immortality from your perspective. But here's the puzzle. Does the multiverse solve the mystery of fine-tuning, or just kick the can down the road? Our universe's constants, gravity's strength, the charge of an electron are exquisitely balanced for life. Tweak them slightly and stars wouldn't form, atoms would collapse. Some argue that in an infinite multiverse, a life-friendly universe like ours was bound to arise by chance. Others counter that this is a cop-out, a way to avoid explaining why our constants are so precise. Now consider an even wilder idea. Could universes be born from black holes? Some theories suggest that the crushing singularity at a black hole's core might pinch off into a new space-time, birthing a universe with physics subtly different from its parent. If true, our own cosmos could be the offspring of a black hole in another reality, a cosmic matryoshka doll with no end in sight. Black holes have long been described as cosmic tombstones, final resting places where matter vanishes forever. But what if there's something far stranger? What if, instead of endings, they're beginnings, hidden inside the crushing depths of a singularity, beyond the point where space-time itself breaks down? Some theories suggest a mind-bending possibility. Black holes might be cosmic wombs, birthing entirely new universes. Imagine a star collapsing inward, squeezed to infinite density, but instead of stopping there, the singularity bounces, rebounding outward in a fiery explosion of creation. Sound familiar? It's eerily reminiscent of the Big Bang, and that's no coincidence. The math behind black holes and the birth of our universe share uncanny similarities. Both scenarios involve a singularity, a point where gravity becomes infinite and known physics fails. When Stephen Hawking calculated that black holes slowly evaporate through radiation, he uncovered a paradox. If a black hole vanishes, what happens to all the information it swallowed? Quantum mechanics insists information can't be destroyed, yet general relativity says it's lost forever. One radical solution: the information isn't gone, it's reborn, encoded in the fabric of a new universe bubbling into existence inside the black hole. Think of it like a cosmic Russian doll. Our universe could be nested inside a black hole from a parent cosmos, which itself may have formed inside another. This idea, called the black hole cosmology hypothesis, flips our understanding of reality on its head. The equations describing a black hole's event horizon, the point of no return, mirror those of an expanding universe. Even stranger, the cosmic microwave background, the afterglow of the Big Bang, shows faint temperature variations that some physicists argue could be echoes of a parent universe's structure imprinted on ours. It's as if the universe is a fractal, endlessly repeating the same patterns at every scale. Now, shift perspective to the origins of everything. If black holes can spawn universes, where did the first one come from? Some theories suggest a chain stretching back infinitely, with no true beginning or end. Others propose a primordial black hole, a singularity born not from a dying star, but from the raw instability of spacetime itself. Either way, the implications are staggering. The cosmos we know might just be one link in an eternal cycle of creation and destruction, where every black hole is a doorway to another reality, and every universe is both the child of a singularity and the parent of countless others. This raises a haunting question. If our universe was born from a black hole, could we someday detect the fingerprints of the cosmos that came before? Some researchers hunt for clues in the spin of supermassive black holes or the distribution of galaxies, searching for anomalies that might betray our cosmic ancestry. Others look for mathematical signatures, hidden symmetries in the laws of physics that point to a deeper, more connected reality. One thing's certain: the line between tombstone and womb has never felt so thin. The Big Bang often feels like the ultimate starting line, the moment when time, space, and matter burst into existence. But here's the twist: the closer we look, the more it seems like this cosmic dawn might not have been a true beginning at all. What if the Big Bang was just a dramatic pivot in an endless cycle, or a ripple in something far larger? Take cyclic cosmology, for instance. Picture the universe as a cosmic accordion, expanding and contracting over eons. Each Big Bang is preceded by a big crunch, where all matter collapses back into a singularity, only to rebound in a new explosion. It's a vision as old as Hindu cosmology, which describes universes breathing in and out over trillion-year cycles, and as modern as Roger Penrose's conformal cyclic cosmology, where the distant future of one universe becomes the Big Bang of the next. Then there's the quantum vacuum, a seething void where nothing is anything but empty. At the tiniest scales, particles flicker in and out of existence, borrowing energy from the fabric of spacetime itself. Could the Big Bang have been one particularly energetic fluctuation in this eternal quantum froth? Some theories suggest our universe might be a bubble in an infinite multiverse, where countless other universes pop into being like bubbles in a boiling pot. String theory takes this further with the idea of colliding brains or multidimensional membranes floating in a higher dimensional space. If two of these brains smashed together, the energy of that collision could have ignited our Big Bang like cosmic flint striking steel. But the most haunting question isn't just what came before, it's why the conditions were so perfectly tuned for life. The universe's constants are balanced on a knife's edge. If gravity were slightly stronger, stars would burn out in a blink. If the electromagnetic force were weaker, atoms couldn't hold together. This fine-tuning problem has led some to propose an almost philosophical answer, that our universe is one of countless variations, with most inhospitable to life. In this view, we're not special, just lucky, like a lottery winner in a sea of losing tickets. Others argue that the fine-tuning hints at something deeper, a fundamental principle we haven't yet grasped. Either way, the Big Bang stops being a singular event and becomes a single note in a symphony of cosmic possibilities, each one rewriting the story of what everything really means. Imagine tweaking the universe's dials just slightly, turn gravity up a notch, and stars would burn too fiercely, collapsing into black holes before life could emerge. Dial down the strong nuclear force and atoms would never hold together. Even the cosmological constant, which governs dark energy, is balanced on a razor's edge. Nudge it higher, and galaxies would have been torn apart before forming. Lower, and the universe would have collapsed in on itself long ago. These aren't hypotheticals, they're real, precise numbers that make our existence possible. The gravitational constant, the mass of an electron, even the ratio of protons to electrons, each is fine-tuned with a precision that defies randomness. This eerie perfection is what physicist Paul Davies called the universe's weird fitness for life. It's as if the cosmos was calibrated for observers, a phenomenon formalized as the anthropic principle. In its simplest form, the principle suggests that the universe must be compatible with life because here we are, observing it. But does that mean the universe was designed for us, or are we just lucky winners in a cosmic lottery? Proponents of intelligent design argue that such precision points to a creator, an architect, fine-tuning the laws of physics like a master watchmaker. Yet science offers another explanation, the multiverse. If infinite universes exist, each with random constants, it's statistically inevitable that one would land in the life-friendly sweet spot. In this view, we're not special, just inevitable. But here's the catch: the multiverse theory, while elegant, is untestable. We can't observe these other universes, leaving the fine-tuning debate suspended between philosophy and physics. Some theorists propose a middle path. What if the universe's constants aren't arbitrary, but emerge from deeper, undiscovered laws? Just as temperature and pressure arise from the chaos of molecules, could life-friendly physics be the natural outcome of a more fundamental reality? This leads to an even deeper question: is information the true currency of existence? From the holographic principle to quantum entanglement, patterns and relationships seem more fundamental than particles. Perhaps the universe isn't fine-tuned for matter or energy, but for the flow of information, a cosmic code where life isn't an accident, but an inevitable expression of its logic. The answer, if there is one, might lie not in the stars, but in the very fabric of meaning itself. What if the universe isn't made of matter or energy, but something far more abstract: information? Think of a computer game where mountains, rivers, and even characters are just code rendered into pixels. Now imagine reality works the same way. Every particle, every force, even time itself could be bits of data in a cosmic program. This is the radical idea at the heart of digital physics, where the universe isn't a collection of objects but a vast, interwoven network of information. John Archibald Wheeler, the physicist who coined the term black hole, framed it poetically, it from bit. In his view, every particle, every interaction ultimately springs from binary choices, like the zeros and ones underpinning a digital world. Quantum entanglement offers a tantalizing clue. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. It's as if the universe is performing a real-time data sync, updating properties across space-time faster than light could travel. This isn't just spooky, it's efficient, like a network optimizing itself to save bandwidth. Even the Heisenberg uncertainty principle, which says we can't measure a particle's position and momentum simultaneously, starts to make sense if particles aren't tiny billiard balls but data points with limited resolution. Now take this further. If reality is computational, what's running the program? Some theories suggest the universe might literally be a simulation, a hyper-advanced civilization's version of The Sims. The idea isn't as far-fetched as it sounds. Video games already create immersive worlds with their own physics. Given enough processing power, why couldn't a future society simulate an entire universe? Philosopher Nick Bostrom famously argued that if such simulations are possible, the odds are overwhelming that we're living in one. After all, there'd be countless simulated beings for every real ancestor. But here's the twist: even if the universe is a simulation, that doesn't make it any less real to us. The warmth of sunlight, the taste of fruit, the ache of loss, these experiences exist whether they're born from atoms or algorithms. The deeper question isn't just what reality is, but why it feels so vivid. If the cosmos is code, then consciousness might be the ultimate user interface, a way for the universe to observe, interpret, and even alter itself. And that blurs the line between player and program in ways that could redefine existence itself. If the universe is a simulation, how would we ever know? Philosopher Nick Bostrom posed this startling question through his now famous trilemma: three possibilities, one of which must be true. Either civilizations never reach the technological capability to create ancestor simulations, or they choose not to run them. Or we're almost certainly living in one right now. The logic is chillingly simple. If advanced civilizations exist, and if even a fraction of them run detailed simulations of their past, the number of simulated minds would dwarf those in base reality. Statistically speaking, the odds tilt overwhelmingly toward us being artificial intelligences in someone else's cosmic history project. Could déjà vu be a glitch in the system, a fleeting memory leak from a past iteration of the simulation? Or take the Mandela effect, where large groups misremember events identically, like Nelson Mandela dying in prison he didn't, or the Berenstain Bears being spelled Berenstein. Skeptics chalk these up to faulty memory, but simulation theorists wonder, what if they're residual artifacts from an earlier version of the code? Even quantum indeterminacy, the way particles stay in superposition until observed, fits eerily well with a virtual world optimized to render only what's being actively viewed, like a video game loading textures as the player moves. Yet Occam's razor slices back. Isn't it simpler to assume our reality is, well, real? Every layer of simulation adds complexity, energy costs, hardware limits, the risk of crashes. And if we're simulations, who's to say our creators aren't simulations too, nesting endlessly like a hall of mirrors? The debate spirals into metaphysics, leaving us with a haunting thought. Whether we're in a simulation or not, the universe behaves as if information is its deepest layer. Which raises one final puzzle. If we are in a simulation, could the architects be watching us? Ancient astronaut theorists have long speculated that extraterrestrials might have influenced human history. But what if these aliens aren't visitors from another planet, but programmers from another reality? What if we're not the universe's only detectives, piecing together the puzzle of reality? Picture a civilization millions of years older than ours, their senses attuned to dimensions we can't fathom, their technology so advanced it bends quantum fields like clay. To them, the fabric of space-time might be as malleable as putty, something to sculpt, not just observe. Reports of UFOs performing impossible maneuvers, instant accelerations, right-angled turns at hypersonic speeds hint at this unsettling possibility. If these craft aren't from distant stars but from higher dimensions, slipping in and out of our perception like shadows through a membrane, then our entire understanding of physics might be a child's sketch compared to their master blueprint. Consider how humans interact with two-dimensional beings, ants for instance. We can scoop them up, place them elsewhere, or even erase their paths with a swipe of a hand, all while remaining invisible to their plane of existence. Now flip that perspective. What if extraterrestrial intelligences interact with us the same way? The infamous Nimitz encounter, where pilots tracked a tic-tac-shaped object descending from 80,000 feet to sea level in less than a second, defies conventional aerodynamics. But in a higher dimensional framework, such movement might be as simple as stepping over a fold in space-time. The real mind bender isn't just whether aliens exist, it's how their very presence could shatter our models of reality. If a species has harnessed dark energy or mastered quantum entanglement for communication, their physics would look like magic to us. Imagine showing a smartphone to medieval peasants. The gap between our understanding and theirs pales in comparison to what might separate us from a Type 3 civilization on the Kardashev scale. Contact wouldn't just provide answers, it would rewrite the questions, forcing us to confront the possibility that matter, energy, even consciousness operate by rules we've barely glimpsed. And yet, despite the cosmic loneliness that haunts our search, humanity refuses to stop trying to model everything. From ancient star maps to the Large Hadron Collider, we're driven by the same irreducible curiosity to decode the universe's hidden language. String theorists scribble equations describing 10-dimensional space. Quantum physicists chase a grand unified theory. Every equation, every experiment is a whisper in the dark, hoping for an echo. Whether the reply comes from an alien transmission or a breakthrough in the lab, one thing is certain: the moment we grasp even a fraction of the truth, reality will never look the same again. The universe runs on two rulebooks, and they couldn't disagree more. Down in the quantum realm, particles flicker in and out of existence, ignoring the rigid laws of cause and effect. But zoom out to the cosmos, and Einstein's relativity paints a smooth, geometric tapestry where gravity bends space itself. For decades, physicists have chased a single framework to unite these clashing visions. A theory of everything that would explain reality from the tiniest quark to the farthest galaxy. The stakes couldn't be higher. Without this grand synthesis, our understanding of existence remains fractured, like a map torn between two conflicting scales. String theory offers one tantalizing path forward. Imagine the fundamental particles aren't dots but tiny, vibrating strings, each note in their oscillation producing a different particle, like a cosmic symphony where electrons and quarks are just musical tone. To make the math work, these strings need extra dimensions beyond our familiar four, curled up so tightly we'd never notice them, like ants oblivious to the third dimension. But here's the catch: string theory predicts 10 or 11 dimensions, and we've yet to find a shred of experimental proof. Testing these hidden layers would require energies trillions of times beyond what our most powerful colliders can muster, leaving the theory stranded in beautiful but unverified mathematics. Then there's loop quantum gravity, which takes a radically different approach. Instead of smooth space-time, it proposes the universe is woven from finite, indivisible loops, a pixelated fabric where even time comes in discrete chunks. Picture reality as a cosmic network, with each intersection representing a tiny volume of space and each link carrying a quantum of area. Black holes in this model don't crush matter to infinity. They hit a smallest possible scale, then bounce back. It's an elegant solution, but like string theory, it struggles with experimental validation. How do you measure spacetime's pixels when they're a billion times smaller than an atom? Amid these heavyweight contenders, a dark horse emerges: emergent gravity. What if gravity isn't a fundamental force at all, but a side effect, like how the swirls in a cup of coffee emerge from countless molecular collisions? Dutch physicist Erik Verland suggests gravity might arise from the way information is structured in spacetime, a cosmic illusion born from deeper quantum interactions. It's a radical rethink, one that could explain dark matter's ghostly pull without invoking unseen particles. Yet critics argue it falters at galactic scales, leaving the mystery unsolved. Stephen Hawking once warned that the greatest enemy of knowledge is not ignorance, it's the illusion of knowledge, a reminder that our grandest theories might be elaborate mirages. The quest for unification forces us to confront deeper questions. Is reality fundamentally mathematical, or are we just fitting nature into the only language we know? Could multiple theories be true at once, like overlapping maps of the same terrain? As we teeter between breakthroughs and dead ends, one truth remains: the universe owes us no answers. Every equation, every experiment is a whisper into the void, hoping for an echo that reshapes everything we think we know. Imagine 6 blind men encountering an elephant for the first time. One grasps the trunk and declares it's a snake. Another touches the leg and insists it's a tree. A third feels the ear and argues it's a fan. Each is certain of their truth, yet each is profoundly limited by their narrow slice of experience. This ancient parable cuts to the heart of humanity's greatest intellectual divide. Do we understand reality by dissecting it into ever smaller parts, or by stepping back to see the whole? Western science has long championed reductionism, the belief that complex systems can be understood by breaking them into their simplest components. It's how we uncovered atoms, then quarks, then quantum fields, peeling back layers like an onion. But reductionism hits a wall when faced with emergent phenomena, qualities that arise only when parts interact, like consciousness bubbling from neurons or life emerging from lifeless molecules. No amount of studying hydrogen and oxygen in isolation explains the wetness of water. Eastern traditions offer a starkly different lens. Hindu Advaita Vedanta teaches non-duality, the idea that separateness is an illusion, and all things are interconnected waves in a single ocean of existence. Buddhist philosophy takes this further, suggesting even the self is a fleeting pattern in the cosmic flow. These aren't poetic metaphors, but rigorous challenges to the Western divide between observer and observed. Quantum physics now echoes this, showing particles have no fixed properties until measured, as if reality itself refuses to be split into neat, independent parts. The tension between these worldviews isn't just academic, it shapes how we probe the universe's deepest mysteries. When physicists hunt for dark matter, they're reductionists at heart, seeking a hidden particle. But what if dark matter isn't a thing at all, but a shadow cast by the way galaxies interact as wholes? Similarly, consciousness studies split between those dissecting brains neuron by neuron, and those who argue mind can't be reduced to mere matter. So is truth singular or layered? Consider light. Newton saw particles, Young proved it behaved as waves, and quantum physics declared it's both, a chameleon changing its nature based on how we look. Perhaps reality isn't a puzzle to solve but a prism to turn, revealing different facets at different angles. After all, even our senses perceive less than 1% of the electromagnetic spectrum. We're like goldfish in a bowl, unaware the water distorts our view, except we can't be sure there's anything outside the bowl at all. We think we see the world as it truly is, but our eyes are lying to us. Every color, every sound, every texture is just an electrical signal interpreted by the brain. Take something as simple as a rainbow. Those vibrant bands aren't really out there in the sky. They're a trick of the light, filtered through the narrow window of wavelengths our eyes evolved to detect. A flower's red petals, they're not inherently red, they merely reflect light at around 700 nanometers, a wavelength our brains translate as red. To a bee, those same petals pulse with ultraviolet patterns invisible to us, like secret landing strips guiding them to nectar. Even time itself is distorted by perception. A hummingbird's heart races so fast that it sees the world in slow motion, while a sloth's sluggish metabolism makes its reality unfold like a dragged-out film reel. Now consider the mantis shrimp, a creature with 16 color receptors compared to our measly 3. Where we see a blue ocean, it perceives a kaleidoscope of hues we can't even name, like a painter suddenly given 1,000 new shades. Or synesthesia, where senses blend uncontrollably. One person might taste the number 7 as peppermint, while another hears violins as golden spirals. These aren't glitches, they're proof that reality isn't fixed. It's negotiable, shaped by the sensory tools we bring to the table. So here's the unsettling question. If our biology filters so much, what are we missing entirely? Dark matter doesn't interact with light, so it's literally invisible to our eyes. Gravity warps space, but we can't see the bends, only their effects. Could there be forces or dimensions brushing against us right now, as intangible to our senses as radio waves were to medieval peasants? Technology offers glimpses. Infrared cameras reveal heat signatures, particle colliders unmask hidden quantum realms. Yet even our machines are limited by the physics we understand. Perhaps reality isn't something we observe, but something we participate in, a collaboration between the cosmos and the strange, squishy supercomputers in our skulls. After all, the universe spent billions of years unconscious before life evolved to witness it. Does a falling tree make sound if no one's there to hear it? Physics says no sound is vibration interpreted by a mind. In that sense, we're not just explorers of reality, we're its co-creators, shaping the answer to the oldest question of all: what is really here? Every time we peer through a telescope or smash particles in a collider, we're not just observing reality, we're bending it to our will. Take the Large Hadron Collider, where protons scream around a 17-mile loop at near light speed before exploding in showers of exotic particles. These collisions recreate conditions unseen since the Big Bang's first trillionth of a second, teasing Higgs bosons and potential dark matter candidates from the quantum foam. It's like rewinding cosmic history frame by frame, except the film strip is made of energy, and the projector is a megaton machine buried under Switzerland. But what happens when reality's secrets are too subtle for brute force? Enter artificial intelligence, a tool that doesn't just extend our senses but rewires how we think. Modern AI sifts through petabytes of telescope data to spot gravitational lenses warping distant galaxies, or predicts protein folds that could unlock the origins of life. Unlike humans, these algorithms thrive in complexity, finding patterns in chaos like oracles reading tea leaves at the scale of the cosmos. Some theorists even suggest I might one day intuit physical laws we've missed, spotting the hidden grammar of reality like a child absorbing language before they understand the rules. Now leap ahead to quantum computers, those fragile behemoths humming near absolute zero. While today's models struggle with basic calculations, their future iterations could simulate alternate universes with tweaked physical constants, testing the multiverse hypothesis not with telescopes but with qubits. Imagine booting up a cosmos where gravity is stronger or the speed of light slower, watching virtual galaxies spin into existence to see if life could emerge. It's the ultimate thought experiment, rendered in silicon and superconductors. Yet for all their power, these tools come with a paradox. The more we mediate reality through machines, the further we drift from raw experience. A neutrino detector buried in Antarctic ice translates ghostly particles into blips on a screen. Gravitational waves become squiggles on a graph. We've traded the taste of starlight for its spectral fingerprint, the texture of matter for scatter plots. Does this make reality more knowable or just more abstract? That's where art crashes the laboratory. When Turner painted sunsets as molten gold or Kubrick framed the monolith in 2001, they weren't just depicting the universe, they were channeling its awe. Art doesn't compete with science, it complements it, translating data into meaning, equations into emotion. A Hubble image of the pillars of creation isn't just hydrogen and dust, it's a cathedral of gas where stars are born. Maybe the truest lens isn't a tool at all, but the human capacity to wonder, to feel small under the Milky Way, and to keep asking what lies beyond the next horizon. Van Gogh didn't just paint stars, he felt them. His swirling, luminous starry night isn't a literal snapshot of the sky, but a trembling, almost hallucinatory vision of cosmic energy. Every brushstroke pulses with movement, as if the heavens themselves were alive. He once wrote in a letter, "The sight of the stars makes me dream," and in that simple line, he captured something science alone cannot: the raw, emotional weight of the infinite. Art like this doesn't just depict reality, it translates the ineffable into something visceral, a language of color and form that bypasses logic to strike straight at the soul. William Blake's famous line, "To see a world in a grain of sand," hints at this same alchemy. A poet or painter can condense the vastness of the cosmos into a single, trembling detail, revealing universes within the mundane. Take the music of Also Sprach Zarathustra, the booming crescendo used in 2001, A Space Odyssey. Those opening notes don't just describe the dawn of humanity, they feel like it, a sonic big bang that rattles your ribs. Or consider Hilma af Klint's abstract spirals, painted decades before Kandinsky, which she claimed were channeled from higher dimensions. Her work wasn't just art, it was a metaphysical antenna tuned to frequencies beyond ordinary sight. Psychedelic experiences amplify this idea. Under the influence of substances like psilocybin or DMT, people consistently report visions of geometric patterns, cosmic unity, and encounters with entities that feel more real than real. Neuroscientists trace these to temporary disruptions in the brain's default mode network, the system that maintains our sense of separateness. When that filter dissolves, the world floods in unfiltered, revealing what mystics and artists have described for millennia, a reality where boundaries blur and everything shimmers with interconnected light. Indigenous cultures have long used these plants as sacraments, not escapes, insisting they open doors to realms science hasn't yet mapped. But here's the provocative question: when science hits the wall of quantum uncertainty or the hard problem of consciousness, could art become our truest compass? Physicists like Bohr and Heisenberg leaned on poetry and Eastern philosophy to articulate quantum strangeness. The Upanishads, with their declaration Tat Tvamasi, "Thou art," that echo the non-duality that quantum entanglement implies. Even the Hubble telescope's images, though rooted in data, are colorized and composited, a collaboration between cold math and human artistry to make the invisible felt. This isn't to dismiss rigor, but to acknowledge that reality may be too vast for any one lens. Science dissects the wave, art swims in it. Together, they form a braid, what theologian Paul Tillich called the depth of reason, where the measurable and the mystical entwine. Perhaps the ultimate truth isn't in equations or canvases alone, but in the tension between them, a dance of precision and wonder, forever circling the unanswerable. Across cultures and centuries, a singular thread weaves through humanity's spiritual tapestry, the experience of dissolving into something vast, boundless, and alive. A Sufi mystic whirls in ecstatic union with the divine. A Buddhist monk sits in zazen until the boundary between self and sky evaporates. A psychedelic voyager recounts merging with a cosmic web of golden light. Though the languages differ, the revelation echoes: you are not separate from the universe, but a fleeting expression of it. The Hindu Upanishads call this Tat Tivam Asi, thou art that. Meister Eckhart, the medieval Christian mystic, whispered of the Godhead, a ground of being beyond even the concept of God. These aren't metaphors, but maps of a territory beyond words, where the ego's walls crumble and the illusion of separation burns away like morning mist. Modern spirituality often strips away the dogma while keeping the awe. The rise of spiritual but not religious movements reveals a hunger for transcendence unbound by ancient texts or institutions. Meditation apps and psychedelic research labs now borrow from monasteries and shamanic traditions, repackaging ego death as self-transcendence and cosmic unity as interconnected consciousness. Scientists like Robin Carhart Harris study psychedelics in fMRI machines, watching brains light up in patterns resembling mystical states described by St. Teresa of Avila or Rumi. It's as if spirituality and science, long estranged, are rediscovering a common tongue, one that speaks in neural networks and gnotic experiences alike. Carl Sagan's famous line, "We are a way for the cosmos to know itself," bridges these worlds. A biologist might call it self-replicating molecules becoming self-aware. A mystic might say the universe wakes up through our eyes. Both hint at a startling possibility: that consciousness isn't just a fluke of evolution, but a fundamental feature of reality, like gravity or light. Quantum physicist Erwin Schrödinger, in his lesser-known spiritual writings, put it bluntly: the plurality we perceive is only an appearance, it is not real. Yet tension lingers. Science demands evidence. Spirituality traffics in the ineffable. One measures, the other marvels. But what if this divide is an artifact of our tools? After all, telescopes can't capture gratitude, and microscopes can't isolate love, yet no one denies these forces shape our lives. Perhaps the conflict isn't between truth and superstition, but between different modes of knowing. The Dalai Lama famously collaborates with neuroscientists, insisting if science disproves reincarnation, Buddhism must adapt. Meanwhile, physicists like David Bohm ponder implicate orders, hidden dimensions where mind and matter twist into one. The existential weight of this convergence is staggering. If spirituality and science are two paths up the same mountain, the view from the summit rewrites everything. No longer just a bag of atoms, you're the universe's way of gazing at its own beauty, of grappling with its own mysteries. Your joy and suffering aren't private dramas, but the cosmos feeling its way forward, an infinite dance of self-discovery. This doesn't answer the why of existence, but it deepens the question, wrapping it in wonder. After all, if the sacred isn't out there but woven into the fabric of reality itself, then every moment, every breath, every glance at the stars becomes a kind of communion. Why does any of this matter? The holograms, the multiverses, the quantum foam? Because the moment you grasp that your morning coffee is made of stardust entangled with galaxies millions of light years away, the ordinary becomes extraordinary. Consider the simple act of breathing. Every inhale pulls in oxygen atoms forged in the hearts of ancient stars, while every exhale releases carbon that might one day become part of a distant planet. This isn't just poetry, it's chemistry. When you see Earth from space, as astronauts describe, borders vanish and an unshakable sense of connection takes hold. That's the overview effect in action, a shift from me to we, where ecological stewardship isn't a chore but a natural response to realizing you're part of a living, breathing cosmos. Then there's the mental alchemy of awe. Studies show that people who regularly engage with vast, humbling concepts, whether through stargazing, deep time meditations, or even psychedelic experiences, report lower stress levels and greater life satisfaction. It's as if touching the infinite puts daily worries in perspective. A fight over a parking spot feels trivial when you remember both cars are hurtling through space at 67,000 miles per hour on a pale blue dot. Psychologists call this the small self effect, a healthy shrinking of the ego that makes room for gratitude and wonder. But here's the paradox: the more we learn, the less certain we become. Does meaning come from finding answers or embracing the mystery? Viktor Frankl, a Holocaust survivor and psychiatrist, argued that purpose thrives in the search itself. Ancient myths and modern science agree. The hero's journey isn't about reaching a destination but being transformed by the quest. Quantum physics mirrors this with its uncertainty principle. The universe seems to reward curiosity, not certainty. So where does that leave us? With more questions, perhaps, but also with a newfound appreciation for the dance between knowledge and wonder, where every answer unravels into deeper layers of why. And just when we think we've glimpsed the fabric of reality, the cosmos whispers, "Look closer, there's more." Light behaves like a wave when it bends around corners, creating ripples of interference. Yet it acts like a particle when it strikes a solar panel, knocking electrons loose one by one. This isn't a flaw in our understanding, it's a fundamental feature of reality. Niels Bohr, the father of quantum theory, put it best: the opposite of a profound truth may well be another profound truth. The universe seems to revel in these paradoxes, refusing to be pinned down by either or thinking. Take the cosmos itself. Einstein's equations describe a universe that's finite yet unbounded, like the surface of a balloon. You could travel forever in one direction and never hit an edge, yet the total volume isn't infinite. It's a cosmic sleight of hand that bends the mind as much as space-time. Zen masters have trained for centuries to hold contradictory ideas without collapsing them into simplicity. One koan asks students to contemplate the sound of one hand clapping, not to solve the riddle, but to dwell in the tension of unanswerability. Another demands, "Show me your original face before your parents were born." These aren't puzzles to crack, but invitations to step outside binary logic, where opposites cease to oppose and instead intertwine. Modern physics echoes this ancient wisdom. Quantum entanglement shows particles can be intimately linked across vast distances, defying our instinct that objects must be either separate or connected. Dark energy and dark matter dominate the universe, yet remain invisible, proving absence can be more powerful than presence. Even time itself resists tidy categories. In our daily lives, it flows irreversibly forward. You can't unscramble an egg or unburn a log. Yet at the quantum level, particles routinely move backward in time, as evidenced by Feynman diagrams where antimatter is modeled as matter reversing its temporal course. The block universe theory takes this further, suggesting past, present, and future all exist simultaneously, like frames in a film strip. Our sense of time's arrow might be nothing more than a trick of consciousness, a way for our brains to navigate a reality too vast to perceive all at once. This discomfort with paradox isn't just intellectual, it's woven into our biology. Human brains crave certainty, sorting the world into neat categories: safe or dangerous, friend or foe, true or false. But reality consistently defies these divisions. A photon isn't sometimes a particle and sometimes a wave. It's always both, its nature revealed only in relation to how we observe it. The universe isn't merely complex, it's fundamentally complementary, requiring us to adopt multiple, seemingly conflicting perspectives to glimpse the whole. So where does this leave our search for answers? Perhaps the deepest truths aren't found in resolution, but in learning to rest in the questions themselves. Like sailors navigating by stars we'll never touch, we chart our course by mysteries that shimmer just beyond reach, each paradox a beacon pointing toward a reality richer than any single truth could contain. Even after centuries of discovery, the universe guards its deepest secrets like a sphinx. Take singularities, those infinitesimal points at the heart of black holes where gravity becomes infinite and spacetime curves beyond recognition. Our equations scream in protest when we try to describe them, spitting out nonsensical answers like divide by zero, errors in a cosmic calculator. Einstein's theory of relativity paints them as gatekeepers to places where physics as we know it ceases to exist, while quantum mechanics suggests they might be knots of pure information, tangled beyond decoding. It's a paradox that humbles even the brightest minds. The laws that govern the universe break down precisely where we need them most. Then there's the mother of all mysteries. Why is there something rather than nothing? Philosophers like Leibniz wrestled with this, but modern cosmology only deepens the puzzle. The Big Bang gives us a cosmic origin story, but it doesn't explain what, if anything, came before, or what sparked the explosion in the first place. Some theories propose a quantum fluctuation in a primordial void where particles blinked into existence from sheer nothingness. Others imagine an eternal multiverse where universes bubble up endlessly like foam in an infinite ocean. But these are just guesses, placeholders for a truth we might never grasp. Dark matter and dark energy taunt us similarly. Together, they make up 95% of the universe's content, yet we've never directly detected them. Are they undiscovered particles, manifestations of higher dimensions, or could they be evidence that gravity itself works differently on cosmic scales? Every experiment, from underground labs hunting WIMP to telescopes mapping galactic rotations, feels like groping in a dark room for a switch we're not sure exists. Even consciousness, the very lens through which we perceive reality, defies explanation. How do trillions of neurons firing in a gelatinous lump of tissue generate the vivid experience of being you? The hard problem, as philosopher David Chalmers calls it, isn't just about brain mechanics. It's about how subjective experience emerges from objective matter. Panpsychists argue that consciousness might be fundamental, woven into the fabric of reality like space or time. But if so, why are only certain configurations, like human brains, self-aware? Nikola Tesla once mused, the day science begins to study non-physical phenomena, it will make more progress in a decade than in all previous centuries. Perhaps he glimpsed what we're only now confronting, that reality's edges might not yield to microscopes or telescopes alone. The tools we've relied on for centuries, measurement, quantification, repeatability, stumble when faced with questions that straddle the physical and the metaphysical. And so we circle back to where we began. Can we ever truly know everything, or is the universe in its infinite complexity designed to keep some mysteries just beyond our reach? The beauty isn't in the answers, but in the pursuit, the act of stretching our minds toward horizons that always seem to recede. After all, a universe that could be fully understood would be smaller than the minds trying to comprehend it. Climbing a mountain doesn't just reveal the view from the top, it transforms how you see the world with every step. The same is true when grappling with the question what really is everything. Each answer we uncover doesn't shrink the mystery. It stretches the horizon further, revealing new questions shimmering in the distance. Think of the first time you learned atoms weren't the smallest building blocks, but were made of quarks dancing in a quantum haze. Or the moment you realized the night sky isn't a static canopy, but a time machine showing galaxies as they were millions of years ago. These aren't endpoints, they're trail markers on a path that never truly ends. There's a quiet humility in this pursuit. Ancient astronomers mapped the stars with nothing but naked eyes and patience, believing Earth stood at the center of creation. Centuries later, Copernicus dethroned us, relegating our planet to a mere speck orbiting an ordinary star. Then Hubble proved that star was just one of billions in a runaway universe, expanding faster than light could chase it. With every revolution, our cosmic address grew more insignificant, and yet, paradoxically, our understanding grew richer. The universe doesn't diminish us when it reveals its scale. It invites us to marvel at the fact that we're here at all, atoms forged in stellar furnaces now pondering their own origins. This journey reshapes curiosity itself. A child asks why is the sky blue and gets an answer about scattered light, but peel back the layers, why does light scatter? Why do molecules vibrate at certain frequencies? And you tumble into quantum electrodynamics, then further into the mystery of why the universe has laws at all. The questions fractalize, each one branching into deeper unknowns. It's like staring into a mirror reflecting a mirror. The reflections recede infinitely, and you're left not with frustration, but awe at how much there is to explore. Perhaps that's the real gift of asking what is everything. Not a final answer, but a shift in how we inhabit the questions. Scientists chasing unified theories and monks meditating on the nature of mind are, in a way, doing the same thing, dissolving the illusion of separateness to touch something larger. Even doubt becomes a kind of compass. When Feynman said, "I think it's much more interesting to live not knowing than to have answers which might be wrong," he wasn't advocating ignorance, but celebrating the vitality of the search. So here we stand on a mountainside of understanding, gazing at peaks we'll never fully climb. And that's the point. The pursuit isn't just about mapping the cosmos. It's about remapping ourselves, learning to hold both knowledge and wonder in the same hand, to see the universe not as a puzzle to solve, but as a conversation that never ends. The next time you look up at the stars, remember, you're not just a spectator, you're the universe whispering a question to itself.